Welcome to the Deep Dive. Today, our mission is to figure out why artificial intelligence is so incredibly good at passing the bar exam, but just terrible at remembering what you told it 5 minutes ago.
It's honestly one of the most frustrating things about using AI right now.
Right. It drives you crazy.
Yeah.
So to get to the bottom of this, we are looking at a really fascinating new paper. It's by Joshua Topkin and David Yang from Supra Research.
Yeah, the paper is titled Supra Cognitive Modes, a Routed Architecture for Agent Memory.
And we have a stack of their notes, the benchmarks, and all the architectural schematics right here.
The main problem we are tackling today is that, well, we've all been conditioned to think of digital memory as a vault.
Like a safe or a filing cabinet.
Exactly. You toss a file in, you lock the door, and a year later you expect the file to be exactly where you left it.
Because it's digital, it shouldn't change.
Right. We assume AI memory works the same way, just binary and static. The data is either in the vault or it isn't. But that model is completely falling apart at the state-of-the-art level.
Okay, let's unpack this. Because as you interact with these advanced AI agents, they are accumulating absolute mountains of data.
Oh, massive amounts.
We're talking hundreds of long conversations, constantly shifting user states, gigabytes of retrieved web evidence.
It's overwhelming for the system.
Exactly. Forcing an AI to shove all of that into one generic, one-size-fits-all filing cabinet, it's causing a massive architectural bottleneck.
The agents are either, getting critical details, hallucinating entirely, or just taking forever to answer you.
And to understand why the machine is breaking, you really have to look at the shape of the questions we ask it.
Right, because when you interact with an agent, the cognitive tasks you're demanding are incredibly heterogeneous. They're all over the place.
I like to think about it like asking a human friend a question.
Okay, I like that.
If you ask a friend, hey, where did I leave my keys? They just do this light and fast factual lookup in their brain.
Right, they just picture the kitchen counter.
Exactly. The answer is just, there on the kitchen counter. Done. Quick and cheap. But if you sit down with that same friend and ask, what's the overall vibe of our 10-year friendship?
Oh, that is a very different question.
Right. They can't just retrieve one single fact for that. They have to actively synthesize a decade of context, emotions, arguments, all those shared experiences.
It requires a completely different cognitive process.
Exactly. And if you force a computer to use the exact same processing mechanism to find your digital keys as it uses to summarize a 10-year digital friendship, well, the whole system just grinds to a halt.
What's fascinating here is that the authors of this paper explicitly define this tension. They actually call it the memory trilemma.
The memory trilemma.
Yeah, it's this permanent tug-of-war in AI deployment between three things: answer quality, response time, and compute cost.
So let's break that mechanism down for the listener. Why is it a trilemma? Why can't we just have high-quality answers that are both fast and cheap?
Well, it really comes down to when and where you decide to spend your processing power.
The compute budget.
Right. Option one is what we call aggressive extraction at ingest.
Okay, what does that mean in plain English?
Meaning, the very second the AI receives a new piece of information from you, it spends a ton of compute power organizing it, tagging it, and cross-referencing it in the database immediately.
Oh, I see. So you're paying top dollar to perfectly organize a filing cabinet, categorizing every single sticky note before you even know if the user will ever ask about those notes again.
Exactly.
That sounds incredibly expensive up front.
It is. It's too expensive for most developers. So they often try option two, which is broad multi-pass synthesis at query time.
So doing the work later.
Yes. Instead of organizing everything perfectly up front, you just dump the data into a giant pile. It's cheap to store.
Okay, but there's a catch, right?
A huge catch. Because then when you ask a simple question like, where are my keys? The AI has to sift through the entire massive pile.
Oh, wow.
Yeah, it has to run heavy reasoning models over all that raw data just to find one tiny detail.
So you've just shifted the cost. Now you're doing a deep philosophical dive through years of archives just to answer a basic trivia question.
And the latency goes through the roof. It takes forever.
Okay, I get the tension now. But wait, I have to play devil's advocate here for a second.
Go for it.
If doing heavy extraction up front is too expensive and doing heavy synthesis at the end is too slow, isn't the proposed solution in this paper, adding a whole new routing layer and a semantic classifier, isn't that just creating a new bottleneck?
That's a really fair question.
Like, aren't we just moving the latency from the database into some complex traffic control system?
That is the exact trap previous architectures fell into.
Yeah.
But this is where Supra Cognitive Modes, or SCM, fundamentally changes the game.
Okay, how so?
They aren't just adding a bloated traffic cop. The paper proposes treating the memory operating point as a per-query control system.
A per-query control system.
Yeah. It is a highly optimized pipeline moving in 3 distinct stages: mode, payload, and procedure.
I really want to walk through that pipeline step by step because it's honestly so elegant.
Let's do it.
So, the AI receives your prompt,
Yeah.
and before it ever even touches the memory database, this thing called a frozen semantic classifier analyzes the question.
Right.
And it assigns the query a semantic label, which they call the mode.
And this classifier works extremely fast because it only has one job. It just categorizes the shape of the required cognitive work.
So it's not trying to answer the question.
No, not at all. It just looks at your prompt and labels it. Is this a single fact lookup? Is it a long-form synthesis? A time-anchored lookup? Or maybe a latest version resolution?
Okay, so it gives it a label. And once it assigns that label, that mode translates into a payload.
Yes.
I kind of imagine the payload as a highly specific briefing folder. Like it contains concrete instructions, filters, and flags.
That's a great analogy.
And that folder gets handed off to the final stage, which is the procedure. This is the actual execution family that dives into the memory to get your answer. But, and I think this is a crucial point of clarification for anyone trying to visualize this, SCM doesn't use 4 different separate databases to pull this off, right?
Oh, absolutely not. If you had separate, isolated databases for every mode, it would cause massive data syncing issues.
It would be a nightmare.
Total nightmare. Instead, SCM uses what the authors call a shared asynchronous substrate.
A shared asynchronous substrate. That's a mouthful.
It is, but it just means it is a single, unified, underlying pool of memory.
The word asynchronous is doing a lot of heavy lifting there, though. How does this substrate actually function mechanically without bottlenecking?
Okay, so when new data comes in from a user, it goes through a mandatory Tier 1 ingest path.
Mandatory, so it happens every time.
Every single time. It's a lightweight, non-negotiable process. It creates a baseline queryable foundation.
So things like basic text chunks, standard embeddings.
Yeah, and extracted relation triples. The point is, the moment that Tier 1 ingest finishes, the system is immediately capable of doing a basic factual lookup.
So it gets the bare minimum filed away instantly.
Instantly.
But obviously, to handle those complex friendship vibe questions we talked about, it needs more metadata than just the bare minimum.
And that's exactly where the asynchronous part comes in. Optional background supplement jobs are spun up.
While the AI is doing other things.
Yes. While the AI is already going about its business answering other questions, these background jobs are just slowly grinding away, caching higher-level signals for that new data.
So what kind of signals?
Things like determining the document shape, or anticipating future key points, or classifying entity types.
But wait, what happens if you ask a complex question about that data before those background jobs are finished?
You'd think it would break.
Yeah.
Yeah.
Doesn't the system just crash because it's looking for a tag that literally doesn't exist yet?
This is the beauty of the architecture. They use nullable fields.
Nullable fields, so they can just be empty.
Exactly. If the background job hasn't finished tagging the document shape, the field is just null, empty. The system doesn't panic. It doesn't block the query.
It just gracefully degrades.
Yes. The AI either skips that specific filter or attempts to figure it out on the fly during the query.
That creates an incredibly resilient design.
It really does. It never traps the user in a loading screen just because some background organizational task is running a little behind.
I love how flexible that is. And there's another detail in the paper about that flexibility that really stood out to me. The semantic labels, the modes, and the actual execution procedures are not strictly one-to-one.
No, they aren't. And the dynamic nature of this is just brilliant.
Walk us through it.
Say the frozen semantic classifier looks at your question and thinks, oh, this is a simple single fact lookup.
Okay.
So it prepares the simple payload. But SCM has these mechanisms called runtime gates.
Runtime gates.
Right. As the payload approaches the database, a runtime gate scans the actual retrieved data context.
The real data it's pulling up.
Exactly. And if it suddenly detects a rat's nest of conflicting relation markers, meaning, the simple fact is actually heavily disputed in your past conversations, that runtime gate can intervene.
Oh, wow.
Yeah. It overrides the initial label, aborts the simple lookup, and forces a much more rigorous, complex, multi-hop procedure.
So it realizes it stepped on a landmine of context and dynamically shifts its own cognitive depth on the fly.
Exactly. It's self-correcting.
Here's where it gets really interesting, though. Now that we have established how the traffic controller routes the question, we need to lift the hood and look at the engine itself.
The actual procedures.
Right, what are these procedures actually doing to the data? The paper outlines 3 major execution families. Let's start with the simplest one, direct lookup.
Sure. Direct lookup handles your fundamental factual retrieval. When you need a specific needle in the haystack, it runs a hybrid search.
A hybrid search.
Yeah, it uses sparse lexical retrieval, specifically BM25 running in parallel with dense embeddings.
Wait, pause on reciprocal rank fusion in those terms for a second.
Let's break it down.
Yeah, for those of us who aren't search engineers, let's translate that. Lexical retrieval, BM25, that's basically just fancy keyword matching, right?
Yes.
Like doing a control F on a document for the exact word keys.
Exactly that. It is highly precise for specific terminology, but it fails if you use a synonym.
Because it's literally just matching letters.
Right. If you search for automobile, but the document says car, keyword matching completely misses it.
And that's why it runs in parallel with dense embeddings.
Precisely. Embeddings translate the meaning of your text into mathematical coordinates. It's conceptually matching ideas.
Ah, so it knows automobile and car are mathematically sitting in the exact same conceptual neighborhood.
Got it in one.
So the procedure takes the top 10 results from the keyword match and the top 10 results from the conceptual match. And then reciprocal rank fusion is just, what, the mathematical blending of those 2 lists?
You've got it perfectly. It merges the lists, re-ranks them based on their combined scores, and serves up the final context. It is incredibly efficient for facts.
Okay, so blending keywords and meaning works beautifully for isolated trivia.
Yes.
But what if the answer isn't sitting neatly in one single document? What if the AI has to connect the dots across 5 different conversations spanning 3 years just to realize that my favorite movie genre completely changed?
Right. A direct lookup would just blindly pull the first mention of a movie it finds. It wouldn't understand the timeline.
Which brings us to the second execution family.
Graph and iterative multi-hop handling.
This one is cool.
It is. This is designed specifically for relation chains and current state reasoning. During that Tier 1 ingest we talked about earlier, the system extracts what are called triples.
Triples, like 3 things.
Exactly. A triple is just a subject, a predicate, and an object, like user like sci-fi or user moved to Chicago.
If we connect this to the bigger picture of how AI agents function in reality, managing changing states is literally the biggest headache.
People change their minds constantly.
Exactly. The facts of our lives update. If I tell the AI I live in Chicago, and 2 years later I say I moved to New York, the AI needs to know both of those facts exist, but it absolutely must prioritize the new one.
And this is where SCM implements a concept called latest revision precedent.
Latest revision precedence.
Right. When the graph planner is actively walking through those relation triples to answer your question, it orders all the conflicting data points by their descending version numbers.
So it sorts them by newest first.
It structurally enforces priority for the newest values.
So it doesn't just guess which one is right. The system architecture literally demands that New York override Chicago for any question about my current address.
Yes. But the critical nuance here is that it achieves this without overwriting the old data.
Oh, so Chicago isn't deleted.
Exactly. It retains the older evidence in the graph. It preserves the provenance, the historical trace of how a fact mutated over time.
That's huge, because you might ask the AI, where did I live before New York?
And if it overwrote the old triple, that memory is permanently gone.
Right, it would just say, you've always lived in New York.
Exactly. So SCM ensures it isn't just an updating database. It is a true temporal memory trace.
It maintains the history of your digital life. Okay, so we've got simple facts covered, and we've got changing relationships covered. What about the heaviest lift of all? The 10-year friendship 5 question.
That requires the third procedure family long-form synthesis.
The big one.
Yeah. This is invoked for incredibly broad requests that span vast amounts of history.
But how does it mechanically do that without just running out of compute?
Yeah.
Like, you can't just feed a 10,000-page transcript into a reasoning model all at once.
No, the context window would shatter.
And the compute bill would be astronomical.
Oh, absolutely. So you can't read the whole transcript. Instead, the system uses chronological sampling.
Okay, meaning it takes slices.
Right. It segments the timeline and pulls representative memory chunks from across the entire history. But more impressively, it utilizes a source shape classifier.
A source-shaped classifier.
Yeah. Before it starts synthesizing, it analyzes the structure of the text it pulled. Is it reading a narrative story, a dense research paper, a messy technical server log, or maybe a mix of all three?
And it adapts its own prompt based on that shape.
Yes.
If it knows it's reading a technical log, it tunes its instructions differently than if it's reading a conversational chat history. It is highly aware of the texture of the data it's handling.
The theoretical elegance of this routed architecture is honestly undeniable. It shifts gears effortlessly, but as with all computer science, the theory only matters if it survives contact with reality.
Exactly. After hyping up these cognitive modes and routing systems, it is time to look at the truth in the data.
The benchmarks.
The authors benchmarked SCM against a production comparator and MenZero version 2, which is a popular open source software baseline. They ran them across 3 major rigorous benchmarks, and the raw numbers are deeply impressive.
The aggregate performance definitely makes a statement.
On the memory agent bench, or MA, SCM hit 61.49%. On the Long-Nevel benchmark, it achieved an 86% success rate.
That's huge.
And on the long-term conversational memory benchmark, known as LOCOMO, specifically isolating the factoid categories, it scored 84.87%.
Wow.
Across all 3 distinct testing grounds, SCM recorded the highest aggregate scores among the configurations tested.
This raises an important question, though. Whenever you see a clean sweep in benchmarking, you always have to read the fine print.
Naturally.
And I have to say, the paper exercises a level of scientific honesty that is quite rare in AI research right now.
I noticed that, too. They placed very strict boundaries on their own claims. They didn't just take a victory lap.
Not at all.
What specifically did they flag as missing from their own data?
Well, there are 3 major caveats. First, they explicitly state that the raw baseline outputs from the competitors were unavailable in their evaluation package.
Okay, meaning what?
We have the final percentage scores for the baseline models, but the researchers couldn't independently verify exactly how those baseline models were prompted or generated under the hood.
So they are saying, we beat their high score, but we can't definitively prove the game was played on the exact same difficulty setting because we can't see their raw code.
Exactly. That's incredibly transparent.
It is. What's the second caveat?
Secondly, the timing boundary is misaligned for the LOCOMO and Long-Nevel benchmarks.
How so?
Those 2 specific tests utilized an offline stage 3 synthesis path to achieve their final answers.
Meaning the system did the quick retrieval online, but then went offline to do the heavy lifting long-form synthesis reasoning.
Yes. And the system only recorded the latency the time it took for that initial online retrieval.
Oh, I see.
The time it took to do the massive offline synthesis wasn't properly persisted in the system records.
So they lost the timer.
Basically. So they can't accurately claim how fast the total process was for the specific benchmarks.
Fair enough. And the third caveat?
They noted a lack of component-level removal ablations.
Ablations, meaning they couldn't just systematically turn one knob off at a time to see what broke.
Precisely. In a perfect experiment, you take this massive SCM engine and you turn off just the semantic classifier, run the test, and see how much the score drops.
Right.
Then you turn off just the reciprocal rank fusion and run it again. Because they couldn't run those isolated ablations, they strictly bound their conclusions.
They didn't overpromise.
No. They state that this paper successfully proves an implementation of a routed architecture. It characterizes the failure patterns beautifully, but they avoid making absolute causal claims about statistical significance.
So they aren't saying, we proved the semantic classifier makes everything exactly 20% better.
Right.
They're saying, we built this incredibly complex V8 engine, we ran it on the track, here are the exact weather conditions, and here is exactly where the engine succeeded and where it completely stalled out.
A perfect way to summarize it.
And honestly, looking at the diagnostic autopsies of where the AI broke is almost more fascinating than the 86% success rate.
Oh, the failure analysis is always where the frontier of the technology is actually revealed.
Exactly. Despite this cutting-edge architecture perfectly routing the queries, the system still failed a portion of the time. Why?
This is the best part.
There is a massive moment buried in the Long-Nevel diagnostics that completely shifts how you think about this whole problem. In their local reproduction, the researchers isolated 73 judged failures.
Okay.
And out of all 73 of those incorrect answers, every single one of them had a specific system flag attached. The flag was hit at k equals true.
For anyone listening who isn't deep into the weeds of retrieval metrics, let's translate that flag.
Yes, please.
Hit at k equals true means the retrieval engine worked flawlessly.
Wait, really? Flawlessly?
Yes. The exact correct piece of memory was successfully pulled from the database and placed directly into the AI's active context window.
So the AI literally had the answer sitting on the desk right in front of it.
Exactly.
It found the needle in the haystack, steered directly at the needle, and still gave the wrong answer.
The authors categorize these as evidence use errors. The architectural bottleneck of finding the memory has basically been solved by systems like SCM.
The writing works.
It works perfectly, but the language model's reasoning engine fundamentally failed to use the evidence properly.
Give me a real-world scenario of an evidence use error. Like, what does that actually look like to a user?
It looks incredibly frustrating. Imagine the system retrieves a very clear note from a past conversation that says, "User is deadly allergic to peanuts."
Okay, good to know.
That text is sitting right there in the working memory. But the user asks, "What should I make for dinner tonight? I'm craving Thai food."
Oh, no.
The AI's reasoning engine gets entirely distracted by the semantic weight of the word Thai, ignores the allergy note sitting right on its desk, and happily outputs a recipe for a peanut sauce curry.
That is wild. So the memory didn't fail at all.
No.
The synthesis of that memory failed.
No.
Or I can imagine timeline errors. Like the system retrieves two events. You bought a car in 2022 and you got a raise in 2024.
Right.
Because those two sentences are sitting next to each other in the retrieved text chunk, the AI hallucinates causality and says, you bought a car because you got a raise, completely inverting the timeline.
That is exactly what the MBA failures showed. The failures clustered heavily around relation chains. You know, the multi-hop fact consolidation tasks and complex recommendations like movie rec.
Where it has to weigh things.
Yeah. If you ask an AI to map out a tangled chain of changing events or weigh competing preferences to make a recommendation, finding the raw data is only half the battle.
It's just the first step.
The language model itself has to know how to logically manipulate the data it is looking at. And right now, it struggles to do that consistently.
That makes sense.
In some of the adversarial tests in the paper, the AI would even abstain, outputting, "I don't have enough information on that," while the very facts it needed were explicitly loaded into its context window.
It's like asking your friend where your keys are. They look directly at the keys resting on the counter, and they say with total confidence, I have absolutely no idea.
It's hilarious, but it's a huge problem.
It really reframes the entire industry conversation around AI memory. We have spent the last few years obsessing over the database.
Just getting the data out.
Exactly. But this paper proves the bottleneck isn't always finding the data anymore. Systems like SCM are getting astonishingly good at dynamically routing queries and instantly pulling up the exact chunks of text you need, no matter how deeply buried they are.
The new bottleneck is the reasoning capability of the model reading those chunks.
It highlights a massive glaring gap between retrieval mechanics and reasoning mechanics. You can build the most elegant routed architecture in the world, but it ultimately serves data to a model that can still stumble over basic logic.
Which is a sobering thought.
So what does this all mean for you? Whether you're a developer building these agentic systems, a business leader trying to deploy them, or just someone endlessly curious about where the technology is heading.
Right. What's the takeaway?
I think the core takeaway from the Supra research paper is that, true, state-of-the-art AI memory absolutely requires dynamic routing. It cannot just be a massive static database.
Completely agree.
If we want agents that actually feel smart, fluid, and contextually aware, they need an architecture like SCM. They need a system that can shift gears, recognize when a prompt requires a quick glance versus a deep multi-hop investigation, and adapt its processing power on the fly without crashing.
That dynamic adaptability is honestly the only way a system prevents itself from collapsing under the sheer weight of its own accumulated context.
But looking at those failure diagnostics, it also leaves us with a really provocative thought to mull over as we wrap up.
Yeah.
If the industry is rapidly perfecting the retrieval side, if routed architectures like SCM can perfectly categorize and retrieve every single fact we've ever told in AI, hitting that hit at k equals true flag every single time, but the reasoning model still failed to logically synthesize those facts.
It's a scary thought.
Are we on the verge of building AI agents with flawless, infinite photographic memories, but absolutely zero real-world wisdom?
It is a fascinating tension to consider. A perfect memory does not guarantee perfect understanding. We might completely solve the filing cabinet problem, only to realize the digital librarian reading the files still doesn't comprehend the story.
A perfect photographic memory, but no wisdom to actually use it. That is definitely something to chew on the next time an AI forgets your preferences. Thank you for joining us for this deep dive into the source material. We'll catch you on the next one.